Aber es ist interessant, ist ein Beispiel von der University of Oulu. Die Scheitel des recent progress on one-dimensional growth conjecture.
And well, thank you, of course, first of all, for this opportunity to give you this talk. And well, Karoli's talk in the morning was very nice, and he even mentioned my name several times, and this is also very nice. But maybe the downside is that he also mentioned the results I'm going to talk about. But anyhow, let's proceed with these plans, even though. We have a list of contractive maps, phi 1 to phi capital N, and let us be on the real line. So everything I'm going to talk now is on a real line. And so there are constructions, and I assume two cases. First, all of these phi i's are C1 plus alpha, so that they are continuous, and they have alpha of the continuous derivatives. And the other case is all of the mappings are similar to this, which means that they have this kind of form. Okay. And then, like Karoli mentioned, there exists, this is a classical result of Hutchinson from '82. We saw that there exists this unique non-empty compact set X, which is invariant under all of these maps. And in the first case, where all of these maps are C1 plus alpha, we say that this X is a self-conformal set. And in the second case, when they are similarities, then we say that it's a self-similar set. Okay. So what are we interested in? So we are interested in basically the size of this X, and how to measure the size. And so the first thing to ask is that what is the dimension of such kind of object? And Probably the first result in this direction is that the Hausdorff regression is bounded above by number S0, where this S0 is the unique number satisfying the following. So if you look at the first level images of this X and look at the diameters to the power S0 and take the sum, then it's roughly the same. So this roughly here is precisely the bounded distortion property what Karel was talking about. It is roughly the same as the sum of the absolute values of the derivatives to the power S0, which is again, well, in the self-similar case, it's precisely precisely 1, but in the self-conformal case, it's a limiting process you have to take. But it's roughly speaking, it's essentially 1. Yeah, and let's prove this. So the half dimension, I think we define that, but what we need to show is that the S0 dimensional delta Hausdorff content is bounded above by something, then we are done. If the something is not, it doesn't depend on delta, then we can let delta go to 0 and we are done. So this is first of all, this is less than we can find a covers of by using these types of construction sets. Thus iterate long enough so that you can be below this threshold delta. So that this is n is chosen so that the maximal diameter is less than delta here. So that's why the definition of the Hausdorff content, we can get this upper bound, and then in a similar kind of calculation then shows that this is roughly the same as looking at this these absolute values of the derivative with power S0. And then some induction argument then shows that this is roughly the same thing as if you take the sum over the first level, and then raise that to the power n. And this was roughly 1 by the choice of S0. So it's basically just using this definition of Hausdorff measure, we can get the claim.
There's how much we shot that. Nothing like it's large, right? The second last approximation that will be like the upper. I mean,
yeah. Up to them. Yeah, some limiting stuff probably appears when you are self-confident. Yeah. So this is like a hand waving proof. Yeah. Okay. So if the strong separation condition holds, which means that this construction piece is disjoint, then it's easy to see that the dimension equals this S now. And the sketch of the proof is again following. So at first there's so-called equilibrium state supported on this symbolic version of this construction, and in this case it satisfies that the measure of each construction piece is roughly its diameter to power S now. Basically, in the seminal case, it's right visible right here. You just use this as a probability vector, and then you construct a measure from there. And such kind of measures, because these equilibrium states, they are the measures which are the candidates to be the dimensions of a maximal measures of a maximal dimension. Then they have the special role here. And now the calculation continues. So basically, we use this kind of density theorem. So we estimate the measure of a ball, and this is of course bounded above by the sum of this method of these cylinders, where we first assume that the diameter of each cylinder is roughly this radius of this ball, and also we don't need here any other construction pieces than those that intersect this ball, so that we can assume that the construction pieces intersect this ball. Okay, so then because we know that the metal has this property, then we can rewrite this sum like this. Which then can be seen because all of these diameters were roughly R. So what we have here is that we are summing over R to the power S naught, and then the question is that how many things we are summing over. And then it's easy to calculate that if you look at if you are interested, you have a strong separation condition, and you're interested in with the construction pieces diameter roughly r, a ball which has radius r, then it's kind of an easy volume argument to show that there cannot be too many of those. Actually, there's a bounded many of those. So that's the argument to show that this is at most this. Okay, but then if you look at some basic book in measure theory or geometry measure theory, then this is a density type of information, which then implies that the Hausdorff measure has to be positive. That's it. Okay. So what was important here in this calculation? So there were basically two things. So that we have such kind of equilibrium state, and then the second one was that here we used this volume argument to calculate the cardinality of these construction pieces. So there's the condition called
the factor used in this place. I remember the time.
Yeah.
Not basic condition, which needs to be.
Yeah. So the first observation is that this previous calculation holds with the open set condition. So the open set condition specification. So the assumption is that there exists an open set whose different images are disjoint, and then these images are also subset of this open set. But when you are using open set condition, so you rarely use the definition, but what you're really using is that is this property that this equivalent property that if you take a supremum over all locations and all scales, then the number of these words I for which this diameter of the corresponding construction piece is roughly r, and this construction piece is intersecting our ball in question. So open set condition is equivalent to the fact that this supremum is finite. And this is precisely what we use here. So if you believe that such kind of equilibrium state exists also in this open set condition case, then the same proof shows that the result also in this open set condition case. Okay, and then there's a result.
Do you use informality here or so these balls of previous
yes,
more mass,
yeah,
more or less around if they are
yes. So basically to obtain such kind of a volume argument requires that you have some information on the shape. For example, if you have like affine mappings, then you could squeeze them like make them narrow and squeeze them together. Yeah. Then there's a result by Juha Perez, Michal Rams, Karol Simon, and Boris Solomia that they proved that open-set condition is actually equivalent for this Hausdorff measure. Hausdorff measure being positive. So this S0 dimensional Hausdorff measure being positive. So this result, this easy calculation shows that the Hausdorff measure is positive, but they showed the converse. Okay. But then, if so the question is that can we handle more difficult cases, and what happens in, for example, in the case where we have exact overlappings. So if X has exact overlaps or complete overlaps, how Karoli called them. But it means that the X is towards I and J, so that the corresponding compositions of maps are the same. And if this is the case, then it means that the dimension actually drops below this S0. And let's put that one. So if it happens that these finite words have different lengths, then we just we replace them by ij and ji, and these are of the same length. Okay, now since one was roughly the same thing as the sum of these derivatives to the power S0 and the whole sum to the power n, which was roughly the same thing as the sum of this n length derivatives of this n length compositions of mappings to the power S0. And if this n is the length of these words, then this actually has to be strictly bigger than the sum where we have omitted this j, because the corresponding maps were the same. And that's it. So if X has exact overlaps, then the dimension drops below this expected value. And the dimension drop conjecture or exact overlapping complete conjecture or complete overlapping conjecture, however you want to call it, then it explains that this is the only mechanism for the dimension to drop below this value as naught. Basically, to put it simply, if you can figure out a way to drop the dimension below S0, which is not exact overlapping, then I'm pretty sure that you will get the nano space.
Excuse me. But if the system is big, then what do you expect to be the diagonal?
Yeah. So the similarity is yes, sure.
And if you throw away one of them,
yes,
then
true. Of course, there are these natural bounds because we are in real line. So we have to be everything. All the dimensions have to be less than 1 in order any of this makes sense. Yeah. Thank you. Okay. So then we talk about this weak separation condition. Thoroughly also mentioned. So weak separation condition is basically opposite condition which allows exact overlapping. And the requirement here is the following. So when in the opposite condition, we calculate the number of different words. So now in the weak separation condition, we calculate the number of different mappings. And the requirement is exactly the same. This is less than infinite. Okay, so let's start looking at what's known for the weak separation condition. So Lau, Nye, and Wang, they proved in 2009 that weak separation property implies that the Hausdorff measure is positive where this S is the half dimension of X. Okay, so if the weak separation condition allows exact overlapping, so if there is exact overlapping, then we know that this Hausdorff dimension is strictly less than S0. So basically, in order to these things to yeah, so this S is most likely it's not S naught. So it's a different S, you know.
Let me ask in this weak condition, we allow infinite seminal overlapping. Can it happen? Of course, of ground class.
So we are just calculating how many different compositions of functions there are that give you.
What can be infinite? I don't know.
Unbounded.
Unbound. I mean,
Yeah.
unbounded plans.
Yeah, you can have a half and a quarter, for example, in an algebraic is two halves.
Oh, I mean, unbounded, of course.
Yeah, it's of course bounded in a sense because if you go to some n level, they are only bounded. They are like a finite mathematics all together, but the number can be definitely can be unbounded. Yeah. Okay, and then we proved with Jasmina on the left and Jose that the opposite implication is also true. And let us sketch the proof. So the first step is to show that the Hausdorff measure and the Hausdorff content, where S is the Hausdorff dimension of the set, they are comparable. Like everywhere, so regardless how you intersect your set. Basically, how to prove this, and if this is not the case,
What is this infinite?
it's a Hausdorff content. So yeah, so in Hausdorff measure you have this delta, and then you let the delta go to 0, and so here the delta is infinite. So you look at the covers that can be of any subset. So the rough idea how to prove this is that if this is not the case, then you have this inequality, and then you take so if this is the set X, then you take a packing of all of size to the power minus n. And then by relying on this IFS structure of the set, then there's for each ball there exists a map that maps the x inside the ball, right? So this is basically because we have an IFS. And then the next step is to make estimates. So we estimate this the Hausdorff measure of this x by the sum of these backing balls. And here we use the fact that each ball contains inside an image of x. So basically, we have again the cardinality of the backing times 2 to the power minus ms times something like this. So basically, the idea is that just you relying on this these backings and then making estimates to get the lower bound for this Hausdorff method, and then similarly, because Hausdorff content is not the measure but it's an outer measure, so we can do similar kind of things. And then the contradiction comes because when we subtract these values, to the power n here, and when we subtract these values from each other, then this is at least, well, this minus this, and here you have to believe that these constants here work for our benefit, so that there's in the difference there's actually a positive constant. So basically, this is just the constant time the content of this guy, which is strictly bigger than 0. And this because this is independent of n, we just let n go to infinity. So then this is a contradiction. So this is really the rough idea how the proof goes, and yeah. Okay, so this is the first step how to prove this result, and then the second step is actually easy because it's a straightforward application of the first step. So this number 1. So number 2 is then easy corollary. So it says that if S is the Hausdorff dimension of X, then the fact that the Hausdorff S dimension of Hausdorff measure is positive is equivalent for x being R force S regular. And R force S regularity means that the Hausdorff S-dimensional measure of any ball. So at the center can be anything and the radius can be anything. So the requirement is that the measure of such kind of ball is roughly R to the power S. So of course, from R force regularity, if you assume R force regularity, then it's a triviality. It's basically the same density argument what I already showed.
It
It can't be in this case. Yeah, good point. Yeah.
in our situation.
Yeah, in this situation it can't be infinite. Yes. Yes, but good point. Yeah, so if X is R force regular, then it's the same density argument that I already showed proves that the S-dimensional Hausdorff measure is positive. And then if S-dimensional Hausdorff measure is positive, then basically just applying this inequality shows that this X is R force regular, because the fact that the Hausdorff measure is positive basically now gives this information, and then we can work with any colors and so forth. Okay, and then the third thing is that if you don't have a weak separation condition, then there exists a weak tangent T having Hausdorff dimension 1. Okay, what is a weak tangent set? So it's basically you just have your magnifier. You have the set here, and you use your magnifying glass that you take a magnification, infinitely many magnifications, and then you just look at Hausdorff limit of those pictures, and that's your weak tangent. And then how to prove this? So if you don't have a weak separation condition, then it basically says that at some scale, so this cardinality bound doesn't hold. So then basically you just start constructing, using that information to construct these kind of magnifications where you have a denser and denser concentration of points of your set. And that's the way to prove that you will find a weak tangent having maximal dimension. Okay, and this is basically everything what we need. Because the conclusion then is that if the dimension is strictly less than 1, then the positivity of the Hausdorff measure implies by this number 2. It implies that X is R force S regular. And if it's R force S regular, and again, remember what that means. So basically it means that at every point and at every scale, the Hausdorff measure of that ball is R to the power S. So basically it implies that any tangent set it has to be also Alphus regular. But in particular, S regular sets, when S is strictly less than 1, cannot have one-dimensional tangent sets. And if this is the case, then this number 3 says that the weak separation condition has to hold. And that's a sketch of the proof.
And we make a break.
Yes. Maybe one thing and then break, because then I switch the topic. Yeah.
Sorry, could you repeat what is the weak tendency?
So you take a sequence of magnifications. So you have a sequence of sets. So you have your self-conformal set is here, and then you take a magnification. So you draw a box there and you magnify what you see. In such a way, you get like infinitely many sets, and then you take the Hausdorff limit in the Hausdorff metric, and that's your weak tangent. Yes.
Is it reasonable to, are there significant problems with bypassing the weak tangent argument by just doing like a ball counting thing? Because you know you have positive measure, right? And if you fit like an unbounded number of images inside a ball, and all those images of positive measure, and also positive measure of approximately ball, there should be some sort of like fidgeting point, right?
I think essentially yes. Okay, so then the first thing. So we basically we prove as a consequence of these things that if we have an extra assumption that the Hausdorff measure is positive after dimension, then the dimension drop conjecture holds. Basically, the claim here is that if the fact that this S is equal to this S naught is equivalent for not having exact overlaps, right? And to show this is easy. So if in the case where S is equal to this S naught, then this Perez, Rams, Simon, Solomia, they show that that the positive of the Hausdorff measure implies open set condition, which then of course implies no exact overlap. Okay, and then the other way around. So if there's no exact overlaps, then well, we know that we just proved that this positive of S-dimensional Hausdorff measure implies weak separation condition. And if there's no exact overlaps, then weak separation condition is the same as open set condition, which of course by their result then shows that the Hausdorff measure at S0 is positive, and since we know that S is at most S0, we have that S equals S0. Okay, and then we have a break for 10 minutes. 10 minutes. And maybe the last thing I want to say is that, of course, as Karoli already mentioned, that this is still a weak result because there are not that many systems that where the weak separation condition holds. And for that, then we need Hochman's result and so forth. Okay, but let's have a break for 10 minutes.
Sasha says, still lots of snow and ice. Or the next floor. Yeah.
I didn't know this.
Winding up.
Actually, half of the rules are given wrong. But they contain the main idea. Exactly. What are that? Should be the idea. But technically strict numbers.
That's fine.
Okay.
Coming from the university at the first, and I don't know what's saying,
Uh-huh.
and I still did. Yeah. It's something for and I like one way.
I will stop 45-ish. I will stop 45 or
Yes.
okay. I'll aim for that.
They all.
Okay. Okay, so that that was that result was for self-conformal set, and it's actually quite funny to say that that's basically everything what is known about the dimension drop conjecture for self-conformal sets. So that's why we have to restrict now for self-similar sets. Okay, so Karl, in fact, already defined these concepts, but what can I do? So exact overlapping is actually equivalent in this self-similar case that this delta n or whatever is equals 0 for arbitrary large n, where this delta n is the minimum of these kind of distances. So we are looking at where the 0 gets mapped, and then we look at with the different mappings, and then we look at the distance of those, and what is the requirement, so that it was required that these are not the same words, because otherwise this would be slightly boring. But they have the same length, and the contraction ratios are the same. Okay, and then we say that the exponential separation condition holds if there exists some number c, so that this delta n is bounded below by c to the power n. Again, for arbitrary large n. So this is really like the lower bound. So it's actually easy to prove that the upper bound always holds. That this number with respect to n, this number decreases exponentially. So this is easy. But if it decreases like precisely exponentially, then we say that the exponential separation holds. And this is the Hochman's condition, this separation condition he introduced. And this really nice result of his show that if this S naught is at most 1, then this exponential separation implies that the Hausdorff dimension equals this S naught. So basically, this gives a way to weaken this strong separation open set condition separation assumptions even more, and actually way more. And again, to point out, because the first hour we talked about these self-conformal sets, there simply does not exist a self-conformal analog of this result. Why I'm emphasizing that this is a really big generalization of these open set conditions and such kind of things. It can be seen in the following. So basically, if this IFS is defined by using algebraic parameters, then this dimension drop conjecture holds. And the proof is rather easy because there's from one applies a bound from the 60s. So basically, it says that if there's no exact overlapping, then Gaussia's result implies exponential separation condition. That's it. Okay, then another result Karoli already mentioned is that the recent result by Ariel Rappaport. And he really he extended this result that here the assumption is that the IFS is defined by using algebraic parameters. So it means that the concept we have this capital N many of similarity maps, and each similarity map consists of basically the construction ratio and the translation vector. And the assumption here is that all of these parameters are algebraic. But Arias Rappaport's result is that he managed to prove that these translation vectors can be anything. So that the assumption is that if the contractions lambda I are algebraic. Then the dimension group consists of holds. Then there's a question that is this exponential separation condition? In fact, Hochman himself asked this question in 2019, if I remember correctly, and he asked if this exponential separation condition is sufficient to actually prove the whole conjecture but he managed to show that. So there are actually two papers, independent and simultaneous, with proof by different techniques. So the first one is by Simon Baker, and the second one is by Balas and myself. And we showed that there exist self-similar sets which that do not satisfy the exponential separation condition and do not have exact overlap. So these results basically say that that unfortunately this Hochman's result is still not well, it is a good result, but not good enough to cover the whole conjecture. And one remark regarding this Baker's result is that he actually used to show this properties. He used to his contraction ratios are actually rational numbers. Which then means that that is Rappaport's result say that because in the Rappaport's result only requirement was that the contractions have to be algebraic and rationals are of course by numbers. So then the dimension of conjecture holds in Baker's example. So therefore Rappaport's result then say that there exists a self-similar set X with half dimension S naught, but it doesn't satisfy the exponential separation condition. Yeah. Okay, then our result was we considered the following system. We had three mappings, and the first map is just lambda times x, and the second map is lambda times x plus t, and the third map is lambda x plus 1. So this is like a looks like a specific type of homogeneous self-similar set constructed by using three maps. And a homogeneous means that the contraction ratio is the same for all. But in fact, it can be shown that by an affine change of coordinates, any homogeneous self-seminal set can be put in this form. And the other remark I want to make is that let's first draw a picture. So this is the first map. This is the second map. Then this is the third map. So basically, this IFS can be also considered to be the projection of a Sierpinski triangle onto some angle. We are in Poland, I think should be correct. Okay, so let us define three sets for related to this this setting, this definition. And the first one is exact overlapping set. So we just collect all the parameters lambda and p. So lambda is the contraction, common contraction ratio, and the t is the translation vector of this second map. So we collect all the parameters. So basically, this is a subset of R2. And the requirement is that the exact overlapping happens. So that phi I for these parameters equals phi j when I and J are different words. Okay, so this is a collection of all the parameters where we can have except all of them.
If lambda you change t. Don't change on.
So I have also changed lambda is also free.
Lambda is also free.
Yeah.
You change both.
Yes. Yes.
Yes, lambda t.
And the second set is we look at all the parameters lambda and t for which we have a dimension draw. So that the self-similar set associated to these parameters has a Hochman dimension strictly less than this S naught. This S naught is also associated to this these parameters, and it can actually be calculated here. So it's log 3 over log lambda inverse. And then super exponential condensation set, or maybe no ESC set. Let's call it C, and it's all the parameters lambda and t for which this this decrease in speed of this delta n is super exponential. Okay, so with this notation, we trivially we have that E belongs to D, and Hochman's results say that D belongs to C. Right. So basically, for in this class, dimension drop conjecture is equivalent for D minus E being 0 or empty set. Okay, but then there's a result by Hochman, 2021, and he proved that the half dimension of E equals 1, and also this backing dimension of C equals 1. And then there's a recent result by I think it's accepted currently. And it says that the Hausdorff dimension of d minus e is 0. And please do not ask about the Hausdorff dimension of the empty set. And then our result with the ballast. It says that C minus E is uncountable. So basically the picture looks like this. These are the set. So we know that E is contained in D and D is contained in C. So this is the picture. And then what we know is that so the union of so the C minus E is uncountable. So basically union of these two outmost annuli or layers that has to be uncountable. And then Hochman say that Rappaport Varjo say that this has dimension 0. And then Hochman say that this has a dimension 1. And again, Hochman say that this has dimension 1. And the dimension of conjecture is that this shaded region here should be empty. So to my knowledge, this is currently everything what we know. Do you agree? Okay, I still have 10 minutes.
Which is sets of dimension 1 are like family of lines. With the parameters lambda t. So question would be how t depends on lambda.
These are really good questions.
And you know the lower bound of E has to be at least 1, just because for every lambda you get T, so you have an exact number, right?
They might be more than.
So there might be more than 1, but then that's what Mike's proof is, that actually it's exactly 1.
We actually have spent some time trying to figure out the structure of this parameter space, but yeah. Okay, so I have still 10 minutes and I was planning to say so Yeah, if I can go a bit over time, then I can explain the idea of our result.
Not much of it.
Okay. Okay, so how to show that how to show our result to this Baronen K, so that in this notation that C minus E is non-empty. So the first thing is to observe that the image of the zero under this these maps, it's actually can be written in this kind of sum. Where this delta ij equals 1 if I equals j, and delta ij equals 0 if not. So this is just like an easy calculation. So therefore, so what we are looking at, so we want to show that so we want to figure out that equivalent characterization for this this condition. And applying this, it actually can be seen that is this kind of guy. Whatever that means. That's not probably important at this place, but the thing is that how we use it is important, and we define a projection so this is like a nonlinear projection. And then we write beta ij to be is delta j3 minus delta I3, delta I2, and it's delta j2. And then we extend it to sequences by the obvious way. like that. And then we define a self-similar set on the plane like this. And with this notation, we can rewrite this condition. So basically this difference being smaller than epsilon is equivalent now for E being being close to this projection of this guy. And why is this important? So basically the whole thing, what we did here, so you can forget all the details. So all the underlying details, but the most important thing here is that in order to find like a super exponentially condensated parameters t, one has to study a nonlinear projections of a planar self-similar set. So we basically transferred the problem of finding this problem of studying IFSs on the real line. We transformed it to a plane by this kind of trick. And for that, we have a lot of machinery what we can apply, and we basically applied these familiar transversality arguments. So maybe I'll write something to achieve this super exponential condensation. Parameter t it must be contained in a super exponential neighborhood of this projection. So what we did is that we transferred the problem into the following. So the task is now to study nonlinear projections of the planar self-similar set k lambda associated to this collection of these similarities. So basically, what we want to do is that we want to understand the projection of nonlinear projections of this guy, and for that we have known tools like the transversality arguments and stuff like that. And we were able to prove the result. So that was all I wanted to say. So thank you for your attention. Implicit in what sense? Like if it's fully explicit in the way you can get out of transversality arguments. So I wouldn't say that the argument gives anything very concrete.
Can you prove that there's any fixed ground which contains uncalculated two, or
I think we tried. I think we tried quite hard to work in this parameter space. At some point, we were thinking that that's kind of the key to go forward. Maybe it is, but I don't think we managed to do anything.
There are lambdas that contain not only contour and magnetic fields, but contour set in the dimension 0. Set of lines, but transversal symptom. Exponential.
Do you know if the dimension drop conjecture holds for the parameter that you get?
No, we don't know even that. I think the only I think the only explicit counterexample for that is if you put together this Baker and Rapoport. But in our case, again, no idea.
There might be a counterexample in your.
Yeah. Yeah, there was also one recent result that this Rapoport vario, they also showed that how was it? So the contraction ratio has to be bigger than some lower bound. Then the dimension drop conjecture holds, something like that. Yeah, I forgot to mention that. Yeah.
More questions? Thank the speaker. But tomorrow,